Howdy folks, welcome to the ElixirConf 2021 virtual track. My name is Chris Ertel, at Ertel and GitHub on Twitter, and today we are going to be talking about the Hitchhiker's Guide to Elixir Performance. Why are we here? This talk is about several things. We're going to talk about performance, and if we want to talk about performance, we're going to need to talk about benchmarking. And if we're going to talk about benchmarking, we probably are going to have to get down into the weeds and talk about disassembly. But the overarching thing we're going to be talking about today, especially in these times with such a critical topic, we're going to be talking about science. Now, the scientific method was something that in the English world we would credit Sir Francis Bacon with in the early 1600s. It has been independently discovered and rediscovered in times preceding that in antiquity in various parts of the world, different cultures and civilizations. Nobody really has a monopoly on knowledge and learning. For us, we're going to say that, again, in the English tradition, this started with Bacon in the 1600s. And it's this very interesting mix of inductive and deductive reasoning where we go and in order to understand the world, first we come up with an observation about, oh, that's a strange thing, or we have a question like, I wonder how we would have the system do X. And then you research it to kind of build some context and build some understanding of the system. And then you form a hypothesis about how you think the system will behave or why you think the system does something. You test that hypothesis by actually conducting experiments or making some changes and collecting data. You analyze that data to kind of identify trends and make sure you understand what's the observed behavior is, and then finally you report your conclusions along with, this is what we observed, this is why we think this is happening. Now, the important thing is that we use science to overcome superstitions, and that means a lot of things to a lot of different people, but in our field, that could be a superstition like, Erlang and Elixir are not fast. Well, or the beam is not for math. To an Erlanger, the beam is for message passing. To an Elixir developer, the beam is for probably serving web requests. Neither party is going to think that it's for math. If you want a performance, you need to rewrite everything in Rust. Well, okay, you need to use NIFs written in C or Rust or Zig or some other language. We're going to push back on all of those today. We're going to dig into them a bit. Why can't we write fast code? Well, I think that we can. We just need better tools, and we need some understanding of things. So we're going to learn some tools today. Our design scenario is we're going to write the world's worst vector library. It's a 2D vector library. We're going to be doing that because it's relatively small. We're not going to worry about most of the operations on vectors other than addition. We're not going to worry about dot products or cross products or anything like that. We're going to worry about adding two vectors together with dimensionality 2. In computer graphics, we might have dimensionality 4. In data science, we might have dimensionality of tens or hundreds or thousands or hundreds of thousands of elements. In machine learning, if you're using NX or something like this, you might have dimensionality of a vector in millions or tens of millions or something like this. For our purposes today, because it just makes a very convenient small example, easy to follow code, we'll be doing vector size 2. So, like 2D vectors. Now, the first part of our method is we're going to pose our question, which is, what is the fastest way in pure Elixir to add two two-dimensional vectors? The next step of the scientific method is we're going to build some context. We're going to research the topic a little bit. And we're going to research the topic by focusing on kind of two things. First, what does it even mean to add two vectors together? And then second, how do we represent vectors? The answers to these two questions are probably going to have a very large impact on how we implement things. So, first question is, how do we add two vectors? For two vectors A and B, we rewrite those as the two column major matrices that they're represented by. A is, AX, AY, 2 elements. B is BX, BY, 2 elements. And then the addition, the vector A plus B is going to be AX plus BX, AY plus BY. Just very straightforward, some of the elements. Now, I promise this is all the math we're going to do. So that one slide was my contractually obligated LaTeX. Now we'll return to our normally scheduled Elixir. Our next question then is, how are we going to represent those vectors? Now, we can represent them as tuples because we know it's going to be exactly 2 elements. of some primitive. Makes sense. We'll use tuples. It's a good fit. In the back we've got Robert is sitting there with LFE going, why don't we just use it as a cons list? I mean, we have lists. Lists are great. We don't need anything else. List of 2 elements. No big deal. And then us web developers, we are probably going to say, okay, it's a map, clearly, because in the web everything is a map. It's a map with a key X and a map with a key Y. And you're done. 2 maps. You probably produce on a map. All is well. So what we're going to do is we're going to blow off the ancient tomes. We're going to go to Mount Erickson and we're going to return with the Erlang efficiency guide. We're going to turn to section 11 verse 1 and we're going to get an idea of the memory sizes. Now we're going to assume a 64-bit system and we're going to assume an Intel architecture. The actual sizes and some of the ranges that these primitives can represent are different whether you're on a 32 or a 64-bit system, and might behave a little bit differently if you are in an Intel architecture versus maybe like an Apple M1 or an Altera or some ARM variant. To say nothing of like a Blackfin or MIPS or more exotic Longsum processor. So looking at this, we see that the numerical primitives we care about, they have different sizes. So a small int, which is any int between approximately negative 5 gorillion and positive 5 gorillion, is represented by 1 word, 8 bytes, 60 bits of which are devoted to actually representing the number. And that's using the kind of tagged memory architecture and the different storage of things that you'll see in the Beam. There's a form for storage on the heap and on the stack, and like how we actually run things. Then there's a storage for storing to disk or interop, external term format. We won't be covering that stuff in this talk. Just know that it's there and know that you can read up on it if you find yourself needing that information. If it's a large integer, which is to say, larger than a small int, it's larger than 5 gorillion in size, that can be represented by at least 3 words, possibly more, because we do support arbitrary persistent integers, which is going to be at least 24 bytes. And then a float, again, is going to look at 3 words, which is going to be 24 bytes. Now, those are our numerical primitives, but vectors are collections of these, in our case, collections of length 2. So let's look at some of the sizes there. So a tuple is 2 words long plus whatever the size of each element is. So that's going to be at least 16 bytes for us. A list of length n is represented by n plus 1 words plus the length of each of the elements. So it's going to be at least 8 bytes. Then we're going to say, okay, what if we put in a small map? So small map is any map less than 32 entries. Any map larger than that uses what's called an H-map, which is a different sort of data structure. If you look at the efficiency guide, you'll see there's a little bit of an involved formula in calculating that size. For our purposes, we're going to assume a small map because we have 2 entries, 3 if it's a struct. And that's going to be 5 words plus the size of all the keys and entries. So we're looking at least 40 bytes. Note that usually for our purposes, when we have a map, we're going to be using atoms as keys. I mean, you don't have to. You can actually use all kinds of neat stuff as keys, but for our purposes, we'll be using an atom. Typically, if you're sanitizing user input, you'll be converting it to an atom, hopefully using 2 existing atom, although as my colleague Lee points out, we can have such large atom tables these days, it's not as big of a deal. It's a fun little bit of trivia. So that's kind of our backing stores and getting a rough idea. And so combining all of those things, so for a vector with floats on a 64-bit Intel machine, our best guesses at memory usage are we're looking at probably 7 words for the tuple approach, 9 words for the list approach, and then 13 words for the map or struct approach. And so now in the method, we're going to form our hypothesis, right? And our hypothesis is that the simplest data structure for representing a vector is a tuple. Not knowing anything else about how it's implemented, we're going to just expect that tuples will be the fastest. So then comes the part of the method where we actually go and we set up our experiments, and then we run them. And so in our case, we're going to have to just code up our different approaches and see which one actually has fruit to show our hypothesis of being correct. So using tuples, it's very straightforward. We create a tuple, we destructure the argument tuples, and then create a new tuple and return it with the sum of the elements. No big deal. Our list is the same thing. Basically, we just traded our curly parentheses for square brackets, and we get back that. Our final version of this is going to be using a struct, which is really a map, and ignoring the slightly clunky syntax for defining a struct, we destructure two structs, we add it, we create a new structure, and push it out. Again, nothing too exciting. And then just for giggles, just to satisfy, you know, the new person to Elixir on every team who really is excited about writing everything as a gen server, because we have message passing, we have the runtime system, we have all of these great tools, we have OTP, and by golly, we're going to use them. We're going to write a version of this where we do all of the addition in a gen server. And so this is a very stripped down gen server. All it does is you initialize it, it registers itself using its module name, and then you can just call, you know, add using our nice little client interface here. And it will add it using what is effectively the tuple mechanism, and then you're set. So if we want to test these manually, we can, and we look in the timer module, and there's a function tc-arity3, which is in module function arguments form, so MFA form, and you can run it. It will return a tuple, the first element of which is the number of microseconds it took to run, the second element of which is the return value of the function. And so we ran this a bunch of times, and the first time we ran it, it took 3,400 micros, which is about 3.4 milliseconds, if I'm minding my decimals correctly. The rest of the time it ran in like, you know, 2 microseconds, 3 microseconds, 4 microseconds. And one of the things we notice about that is that those times are all over the place. And if we really wanted to do a good experiment, we would have to run that a whole bunch of times. And the reason we believe that to be the case is we believe that we're going to have some outliers that we can just throw out of hand, and we're going to make some guesses that, due to the, you know, statistical behavior of our noise and of measurement error, it's normally distributed. There's a bunch of hand-waving statistical things that say, look, as long as we take a whole bunch of measurements, it's all going to come out in the wash, and we'll be able to identify a distribution and run statistics that give us the true representation of reality. So that would be pretty fun. That would be a fun project. We're going to wrap timer TC in some code that actually looks at, you know, generating these values and maybe does some statistics, and that's good fun. But we might also have to worry about initializing the values. We might have to worry about, are we having the correct core affinity or the correct scheduler behavior or the correct process behavior? It can be finicky, so that's why we have something called Benchy. So this is an example script file that we use with Benchy. And the first part of the script file is we're just going to alias vector2d as v, just to make life easier to click on stuff. We're going to have our definitions of the tuples, the lists, and the structs we're going to be operating on. Looking at the tuples as an example, we just go from 1 to 1,000, so we're going to make 1,000 different ones of these. Each one is going to be a pair of vectors. The first vector is going to be in by n, and the second one is just n minus 1 by, n minus 1 plus n plus 1. Just to give, like, you know, some actual numbers to bang against. If we just initialize it to like 0, for example, I might worry that an overzealous compiler might just elide any sort of additions. So this gives like a little bit of grist for the group. Now, then what we have is we go ahead and we're going to start off our gen server to make sure it's running. And then finally, we just invoke benchy.run. Now, benchy.run is an arity2 function. The first argument is a map, which has a scenario name, followed by the function that it corresponds to. Now, the function here is a arity0 anonymous function. It supports up to arity1 if you need to pass in inputs. And I want to say arity2, although I may be mistaken on that, if you need to do any sort of pre-processing. You can additionally, instead of passing in functions, you can pass in tuples, and if you consult the documentation, that will tell you how you can specify setup and tear down for each one of the testing scenarios. And then the second argument is a keyword list, and that contains many different things. In our case, that contains time, which is how many seconds to run for, memory time, how much time to time memory allocations for. You can specify formatters. So Benchy comes with a JSON formatter, and I believe a console formatter, which we'll be using today. And then you can also get like an HTML formatter for it, which gives these nice little embedded web pages you can kind of view your results on. So each one of these scenarios, when it runs, it's going to take our already generated values, and then it's going to throw them into an enum map, and we're just going to run the function over our values. Now, it's important that we did all of this outside of the actual timing, because if you don't, if you don't somehow warn Benchy about it. If we had, decided to replace tuples here with that for loop or, inline the generation or something, we would be timing the generation as well as the actual stuff that we cared about. So it's incumbent on us to pre-process all of this stuff. And we go ahead and we're going to execute this function and we run it. And so we're just going to go ahead and I'm just going to run the benchmark. Benchy is going to go and figure out my operating system, which is Linux. It's going to find out that I'm on a pretty beefy, like first generation Ryzen chip. I've got plenty of RAM. I'm running on Elixir 1.12.3. I'm running on Erlang 24.1. It's going to double check my settings. The most interesting of which here is that first, we don't have multiple inputs specified. And what that means is that Benchy is capable of running a collection of scenarios. So you'd say, okay, I would like to test the tuples and the lists and the maps, but I would like to test it with, one vector, with 10,000 pairs of vectors, with 10 million pairs of vectors. And we're not doing that for simplicity's sake, but you totally can produce more interesting testing scenarios. Finally, there's the parallel setting, which says we're going to run one of these at a time. We're going to do all of these tests back to back to back to back. Now that's important because if you have multiple processes that are each running tests concurrently, you can have weird knock-on effects on your system. If there's any sort of resource that might be under contention or anything else, that can be a problem. So we run them back to back. Now it's going to benchmark these, and the results that we get back, we see that tuples went ahead and they were absolutely the fastest. They had something like 50,000 instructions and iterations per second. GenServer, as expected, was dog slow. It actually breaks it down for us here. It's like almost 2 orders of magnitude slower. List is close to tuples, but definitely still a little bit of a hit, and structs were almost 3 times as slow as tuples. And then finally on a memory usage, this is where it becomes really obvious. There's a non-trivial difference in memory usage for lists and structs. And that's kind of interesting, and when we see the bytecode for that, it'll make a little more sense. And then GenServer is, again, like just gnarly memory usage. So, we've now done, and actually bled over a little bit into the analysis section where we've taken our data, taken our measurements, which Benchy did internally, and then Benchy ran the analysis for us. So that's pretty neat. Unfortunately, it's not enough, right? Having the notion of the distributions is good, but we also want to have a little bit more context for why did we get what we get. And so let's dig in a bit deeper. And the way to do this is to actually dig into the BEAM files that get emitted. So you have your Elixir code, you run it through the compiler, and then after a bunch of things and steps internally, it emits a .beam file. That .beam file is what is then fed to the interpreter, and the interpreter will actually do additional optimizations, what are called people optimizations, dead code elimination, and things where it looks for, the kind of the last leg of cleanup it can do before executing your code. But for our purposes, the .beam is what we want to look at because that bytecode is almost as close as you can get to what we'll be running. Now you can use Erlang disassem.file in order to actually read a binary and give it to you. And so what we're going to do here is we're going to go ahead, we're going to open that file, that BEAM file. It's going to give back a binary blob. And then we're going to feed that binary blob and inspect it. And that's going to give us this very neat set of, it's a BEAM file, here's the module, and then all of these chunks for it. And that's cool. Unfortunately, I use VS Code, and I like having nicer interfaces. So Scout 119 has a plugin called BEAM Dasm, and it will actually give you a friendlier version of this. So remember, here's our source code for the tuple version, and then our emitted bytecode is this stuff right here. And the first thing we do is we're going to check the arguments. So x sub 0 refers to, at this point in this, the first register, which is the first argument, and there are up to 1024x registers. There are also something called y registers, which refers to slots in the stack. The BEAM itself is a register machine with 1024 registers as well as a stack, which is used for, I believe, handing stuff between functions. The work we're doing here doesn't require that, so you're not going to see any y registers mentioned. So the first X register here is we're going to check that it's a tuple, and we're going to test that it's a tuple of arity 2. We're going to do that same thing for the second one. So we've kind of validated what has been given to us as functions arguments. Then we're going to go and we're going to pull out the first element of that first tuple and store it into register 2. We're going to pull out the first element of the second tuple and store it into register 3. Then we're going to go ahead and we are going to say, okay, we want to invoke a function. If it doesn't work, throw an exception and blow up. Otherwise, we're going to go ahead and execute Erlang plus. So we're going to actually add these things together. We are going to blow up and consume. I think we need to keep 4 of these on the stack if we need to garbage collect. We're going to add registers 2 and 3 together and store it into register 2. Then we do the same thing for the Y component. So we're going to grab the second component of registers 1 and 2, and then we are going to go ahead and again add those together and store them into register 1. It's all 0-based indexing, so I apologize for that weirdness. We're going to test the heap. We're going to make sure that we have 3 words available to us, and failing that, we are going to say, okay, garbage collect if you have to, but make sure that our first 3x registers are preserved, and then we're going to go ahead and shove the resulting value into the first register x0, and that is also our accumulator, so when we hit return, we're going to push it up. So very quickly, that is us talking through the assembly, and that's like actually what the beam is going to do when it's running this code. So doing it for list, it's the same thing, except notice here that the first thing we do is a whole bunch of, are you a list? Are you actually a list? Do you contain lists? What's up with those lists? So there's a bunch of that work. And then here, the map version is again similar. We're going to do one thing that's kind of neat is you have this instruction get map elements, and what it does is it can actually take this nice interleaved array of keys and then where to store them when it looks it up, and so that's kind of neat. And you'll also see here this kind of interesting bit where it's going to pull out whatever's in the struct field, and then the next thing it does is it says, hey, is that struct field set equal to your Elixir vector2d struct? And that is how we implement this check right here. So that's kind of slick, because if you remember the way that we do structs in Elixir, they are maps with that struct key set. So the gen server, the bytecode I'm just not going to show. It looks very similar to the tuple one for the actual addition part. The rest of it is a bunch of mixins. So, what are we seeing here? We're seeing that the struct variant has the fewest opcodes, but it's extremely slow when we actually measured it. Why is that? Well, some of those opcodes are kind of chunky, right? Like they do a bunch of stuff. They're not just testing a value, they're doing a bunch of destructuring or other things. Now, the list variant uses fully half of its opcodes for doing error checking. All of the variants do garbage collection, which is kind of interesting, right? Like they actually have several points where even if we're just extracting a couple numbers and then smushing them together and setting them back out again, we're still pausing and giving a chance to do garbage collection using the gcbif2 or the test heap ops. And then finally, the tuple variant uses the fewest registers. That I think is kind of interesting, right? Several of these use like 6 or 7, tuple uses 4. So which of these matters? Well, I'm pretty sure that what makes the tuple fast is that the registers it uses are the fewest, and what makes the struct and list variant slow are that they either do a whole lot of extra error checking, I mean they probably kind of have to, or they use instructions that are just heavier weight. So at this point, we can now conclude that with Elixir 1.12.3 and Erlang 24.1, on x64 Linux on an Intel architecture, with some small integers, individually, tuples are the fastest way to add 2D vectors. And we believe this to be the case because we use fewer registers and we use less memory. Now, I want to say there that, again, we had to be very precise and we can't generalize those results. If we do, we're going to have to change it. So, look, there's no optimization without experimentation, right? That's just superstition. If we are going to say that something is faster, then we actually have to do it. Like the actual work to testing it. And it's tricky to do that work. We have to make sure that we understand exactly what architecture that we're on. We have to make sure that we're testing exactly what we think we're testing. We have to make sure that we're warming everything up and that we're doing it with a clean environment. But all of this is great because it means that we have the power to write performant code. We can make efficient code on Elixir and on Erlang and on other, on LFE and other things. We have the tools to write fast code, and we don't have to necessarily leave our tooling behind. We don't have to leave our languages. We just have to put in a little bit of extra work. And today we saw the science, and I'm going to leave you with the engineering, and the engineering is what's up to you. Engineering is science with cost in the equation. Engineering is science when you have a budget. And as a developer, does your day include time between meetings and progress reports and code reviews to do this extra benchmarking? Is your project a project where you're sending people into space, and you need to make sure that everything is like hard real time, and like so you're going to put in the hours to profile this. Are you a web developer just putting up an MVP and it might not matter? Then maybe it's okay to kind of cut corners and not put in this extra effort on the code. But I will caution you, and I will caution all of us as an industry, that inefficiency is ultimately paid for. In the short term, it can be paid for by having a test suite that takes a long time to run, by having a compile that takes forever. In the medium term, it can cost our employers money and cost, if we're self-funding ourselves money, because we're paying for servers to deal with code that's not running as fast as it could. And in the long term, it's our kids and our grandkids and future generations that are paying for it when maybe the water level has raised because the glaciers have melted, because we wasted a bunch of heat and energy on these poor little rocks with, heated registers trying to do code that's suboptimal, right? We spent a lot of time in sorting or in addition or math that was just inefficient because we didn't profile it, and enough of us did this for long enough that it hurt the planet. So, the engineering is up to you, and I hope that today we talked about some things in this, Hitchhiker's Guide, so you can say, hey, like, I'm empowered to do good engineering, and I'm empowered to make the world and my code a better place. I'd like to thank my colleague Lee. I'd like to thank several people and organizations and specific contributors and kind of keepers of arcane knowledge. I would even like to thank Ericsson for documenting at least several parts of the way that BEAM is implemented. This is all a group effort. We're all in this together, and I'd like to thank everybody that helped me get here. Finally, this is time for our question and answer period. So if you have any questions, I would be more than happy to answer them. Thank you.